Yes, thank you, Mike.
All right.
Yeah.
Good morning, good afternoon, and good evening, wherever you are. So, thank you for this invitation, Juan, and thank you everybody for joining in. My name is Aaron Pereira. I'm from the University of Adelaide in Australia, but the last 7 years or so, I've been at NASA's Jet Propulsion Laboratory in Pasadena, California, working on space-based sensors, on various missions. Most of the focus is on Mars, but today my topic is for Earth observation, so space-based sensors for Earth observation. Just to give you a bit of an idea as to the general context of how this project came about, the US and Australia has been collaborating in space for nearly 70 years, right? So, and we've supported US space missions since 1957. So if you saw Neil Armstrong coming downstairs and, taking his first steps on the moon, it was received by an Australian ground station in Parkes. And that has continued over the years with the Deep Space Network facility in Canberra. It's one of the three that NASA has got around the world, Canberra, Goldstone, and one in Madrid. So we are the only one in the Southern Hemisphere. So if you've seen or heard about Voyager lately, uh, the Canberra facility is the only one that can actually track and listen to Voyager. So we play a very crucial part in NASA's deep space exploration program. However, we've never had any joint assets in space. So we've supported NASA with ground stations, but not a single asset, civilian asset actually in space. Military-wise, we kind of joined at the hip. We share many satellites and technologies and control and command systems together, but not in the civilian side. So for joint assets, this was like the genesis of the program that I'm going to talk about. Basically, to develop Australian capability through international partnership. And one of the crucial elements that we looked at in Earth observation is obviously fires, because Australia fires pretty bad with bushfires. And I'll talk a bit more about that. And recently, you've probably seen how Greece is battling bushfires, and California, where I am, it's quite bad as well. So this was quite topical, and we want to look at technologies in space that can help monitor, predict, and support firefighting activities. So this is a multi-center program, actually with NASA's Goddard Space Flight Center, which is the NASA lead center for Earth observation missions, and NASA's Marshall Flight Center, along with an Australian university. So basically align Australian programs with the space agency's strategic plans, build up capability, look at science goals because that's how NASA works, and provide a pathway to build up sovereign capability in space, especially for natural disasters, so Earth observation missions. And we want to grow STEM, right? We want people like you around the world, young people, to be interested in space, to train themselves and to employ them in the industry and to strengthen the bilateral relationship, or I should say quadrilateral relationship, among the countries involved. And the best way is to have an asset in space. There are multiple universities involved. These slides are slightly a bit old, so there are other universities involved, but the original consortium was 4 universities that you've seen here, plus NASA Goddard at Greenbelt and NASA Marshall at Huntsville in Alabama. So I'm going to talk a bit about bushfires. Why bushfires? Because in the last bushfires in Australia in 2019, 2020, 35 people were burned to death, right? And there were many others who died because of smoke inhalation, asphyxiation, and things like that. Just under 200 people died as a direct result of that. Well, thousands of homes destroyed, and the cost on the industry is quite humongous, at least about $5 to $6 billion, they think. And a lot of insurance payouts, right? And some of the plants and animals, they never recover, right? They don't come back. So that's quite devastating to the industry and to the flora and fauna as well. So it's not just an Australian problem, it's a global problem. And you can see the fire rate of the radiative fire index for the over 2020. So world is getting hotter, obviously, climate change and all the problems associated with this. It's quite real. So we need measures to tackle that. And now coming back to the consortium, we can see the NASA centers there, the universities, and you have science partners at the bottom where all the data gathered by the satellite or the asset in space is analyzed and reported. And you have all these other agencies that are involved. It's kind of complicated, but I thought I wanted to show this because any mission, it's not straightforward. There's too many stakeholders and you have to manage them. As a matter of fact, launching satellites, it's easy. It's managing these stakeholders. It's the most difficult bit. And the capabilities of the consortium are quite considerable. The four universities between them have got at least 150 years of space background and heritage. And you can see on the sandpit, that's the extraterrestrial lab at University of Adelaide, where they test out rovers. So you can see those the granules, the sand particles. It can be tailored to the environment. It can be Moon, it can be Mars. And at Griffith University, you have adaptive additive printing. So you can print out stuff very, very quickly. 3D printing, all that sort of stuff in metal, in plastics, carbon fiber, all that sort of stuff. And the UTS Tech Lab, we have shakers, bakers, all that sort of stuff that you need to test out the satellite, right? Before you fly it. So to qualify stuff, up to 500 kilograms, a satellite weighing up to 500 kilograms can be tested there. And at UNSW Canberra that you see in the bottom right, extreme right, it's the concurrent design facility. So 1/3 of Australia's satellites has been flown or built, conceived, built and flown by that university. And you can see the facilities there, including the control center. So consortium has considerable capabilities. And this is a bit about the UNSW Canberra. So multiple spacecraft has been flown by this university, including many defense missions. One of the missions that they have is the M2A, M2B, which is like formation flying, which is probably one of the most complex and complicated CubeSat that has ever flown. And they've had multiple spin-offs as well. So as I said, significant shake and bake facility. I mean, all the ground stations that you need for a mission, including S and S, UHF, C, and Expand ground stations. I mentioned the formation flying, and you can see there the M2 mission. It's extremely complicated. It was a defense oriented funded mission, and you can see, you can go look this up if you want. So if you Google M2 mission UNSW Canberra, you will see all the details. And one of the things that they have demonstrated is the onboard processing capability. So you can, which is kind of pretty topical in this day and age or right now as we speak, because you don't want to downlink everything that you see, right? When your sensors pick up stuff, you don't want the whole thing to be piped down to earth. You just want the very limited minimum amount, because you want to process what you see on board and send that down as packets, because otherwise your battery and your data is just going to be too much, and you don't want that. Now, coming to the mission itself, obviously the objectives, it serves as a pathfinder. It's a CubeSat, so it's not operational, but you want to show the capability that it can bring, right? And you can see the instrument itself on your left-hand side. And on the right-hand side is the imagery. It's a false image that it flew on the International Space Station a few years ago, and it took images of Australia when there were bushfires. And you can see that on your right-hand side. It's called the Compact Thermal Imager, CTI. It's also available on the web, so you can go Google it, and you'll find the details of these. And you want to look at 500-kilometer sun-synchronous orbit, polar orbit, you know. And there's a critical observation gap that it needs to look at, and that's what we're targeting in this mission, so to speak. So this is obviously, you can see the imager here with the telescope. So you can zoom right up, and the detector itself is called superlattice structure, and it's extremely stable and it is flown. What does that mean? It means it doesn't require calibration like many other bigger instruments, but the capability is just as equally good, you know. And it can be combined with other instruments to give you a much holistic view of what you're seeing, you know, and you can combine that with AI, and it becomes even more powerful, especially when you want to measure fuel loads and things like that, right? So the predictive algorithms kick in and give you an understanding of possible time as to when the fire would break out and how bad it's going to be, you know, that sort of stuff. Now, coupled with the thermal imager, you have a lightning detector, and you might be wondering why lightning detector, because 80% of fires in rural Australia are caused by lightning strikes, you know. So you want to detect that. And once you detect that, you want to characterize the lightning or where it had struck, and to get an understanding of this whole chain. So from the lightning strike to ignition and to the fire spreading. And that's why you have a lightning detector. And NASA's Marshall Space Flight Center is the lead center for this instrument. And obviously you see a rendering on the left-hand side of this lightning detector. It's extremely compact. So size of a 2U, if you're familiar with CubeSat terminology, it's a 2U. It'll fit in nicely. And it's tuned to a wavelength of about 777 nanometer, which is the atomic oxygen triplet line. And it's traditionally used for lightning mappers. It's a CMOS imager. It's a derivative of LIS that is flown on the International Space Station. And also a NASA GOES 16, 17, 18. So it's the heritage instrument sits on the NASA, the NOAA's GOES satellite in a geosynchronous orbit. Oh, so it's kind of a derivative of that. So there's some flight heritage with this. And I mentioned the onboard processing, and you can see the edge computing modules on your left-hand side. It's a Jetson GPU, but with algorithms that have been developed basically for image processing, recognition, as well as characterization, you know. And as I said, one of the major objectives is to try and predict fuel loads, right? So if you know the content of the forest or the bushfires or the bush, so to speak, you can try and assess how much potential fuel load there is, and try and send firefighters to do controlled burns or set in mitigation strategies to control the fire. So, and you can see the telescope that goes with it. It's a rendering of that. So, and you can see it mounted as in there as well. At the bottom, you have a dosimeter from Griffith University. It's also has got heritage, which is flown on JPL's, or NASA JPL's Mars exploration rover back in 1997. What does a dosimeter do? It picks up the radiation. It tries to tries to understand what the electron density is and all that sort of stuff. So, and you need that because you don't want your instruments working when there's high flux, electron flux or particles in there, right? So that's why it's just a PCB, but it's crucial. Now, along with that, you have, so all of the previous instruments are kind of custom, specifically designed for this mission of previous missions, which have been tailored for this mission. Along with that, you have a visible imager, which is from Gecko, from Dragonfly Gecko. So we've been talking to many stakeholders, and one of them obviously is the firefighters, right? So they want to understand the direction of the bushfires, and one way to do that is to detect the direction of the smoke plumes, and you can do that with a commercial off-the-shelf detector, and which is what it does. This also has got heritage, so you can buy it and you can fly it straight away. And the spacecraft itself is a Hex-20's 12U, and you can see on the left-hand side the specs. And in the middle, you see how it's a rendering of a fit check with the telescope and other avionics stack and all that. It's not perfect. As I said, it's just a baseline 12U. It might go up, might be bigger, 16U, maybe 20U. But you get an idea as to how it fits into the spacecraft, right? It's a simulation of the platform queuing and also downloading data down to this ground station. So obviously roles and responsibilities. Obviously it's an Australian-led mission supported by NASA. And Australia would manage most of the instrumentation, integration, launch, and all that. And the fire science side of things is given by NASA Goddard. And the lightning detector obviously comes from Marshall. And the instrumentation too comes from NASA, right? With heritage. Basically, it's like a pathway for creator program. And the responsibility itself, you can see, I mean, if you've been involved in various missions, you will see how everything is broken down. Along with Australia and US, the launch obviously or most likely would be with ISRO on the PSLV launch vehicle, and the ground station support provided by both New Zealand and Japan. Now, you might be thinking that's all kosher, nice and well, but what's the future? Future obviously is to have lots of them, right? Lots of these spacecraft that you can cover the whole country. So within ignition of say 5 minutes on the ground, it'll be picked up by a space-based asset, and you need lots of them. You need about 72 spacecraft actually to cover the whole country or areas of interest that we want to do. And it can be done through satellites that are optically interconnected, basically have optical terminals with lasers so they can communicate. And so they're extremely flexible, but at the same time, you can move them around so they can form a swarm. So if there's areas of interest that you want to zoom into, multiple spacecraft can come in and have a much better field of view, right? You can stitch the images together so you can synthesize any aperture you want, so to speak, if that makes sense. And gives you an example here. Now, where does this fit in the larger scheme of things? I mentioned about the swarm concept, but where does it fit into the existing or future constellation? You can see the wildfire sat from Canadian Space Agency and the sea fires. So this would supplement all those missions, so And that's how it should be, right? Because bushfire affects the whole world, not just Australia. So we want to have a global system in place that people can share assets and fight fires. So just to summarize, this is a US-Australia demonstration of first space flight, basically to develop indigenous capability and undertake people-to-people exchange, and hopefully it will be the first step towards something bigger and better, you know. And what does that entail? So pathway for future collaboration. So we are right here with the CubeSat, but we want to look at much bigger things, hopefully a small sat, and then go interplanetary. So the first two that you see would be LEO or MEO missions, low Earth orbit, medium Earth orbit missions. But then you look for interplanetary, maybe Mars, some of the icy moons, Jupiter, Saturn, you name it, you know, and beyond. That's the plan. So I know I went through the slides quickly, but I'm happy to take any questions right now as we speak. So,
okay, guys, any questions? I have one question.
yes.
What about the space debris? Do you have an idea to see
Yeah.
how complicated is that?
Okay. I didn't put out the
And how
full.
you are going to,
Yeah.
how you are going to solve that issue, right?
Yeah, so I didn't put out the whole concept of operations. So so for people who don't know what space debris is, space is extremely congested, right? So you have thousands of former satellites floating around and other debris, rocket parts, you know. I think NORAD tracks about something like 11,000, and some of them from a size of 5 centimeter all the way up to much bigger geosynchronous satellites. To answer your question, Juan, so the life of this CubeSat obviously is going to be something like 12 to 18 months, right? And then you will deorbit into a safe deorbit. And then slowly it'll burn up on re-entry, you know, so there wouldn't be any debris. So it'll completely burn up, yeah. So if that makes sense.
Any rules for that for the future, really? There is
the sustainable space is like the theme right now, you know,
right?
and people are talking about it, and they're talking about it G7 at various UN bodies and within the agencies itself. One of the issues we find is you look at the ISS itself, right? A few years ago, there was an anti-satellite test that happened, and it created a lot of basically someone just, I'm not going to name who, but someone sent a missile and blew up a defunct satellite, and it created thousands of debris, very, very small ones, but it hit the International Space Station. Even though they're very small, the velocity that they carry is tremendous, right? It can cause serious damage. And people and the astronauts on the International Space Station had to go into their safe rooms and things like that. So it's pretty serious, and people are talking about it. And it's there are, I wouldn't say rules, but they're like, you know, agreed principles as to how and when it should be safely removed, you know. And people, or at least commercially, they have space tugs for such purposes, you know, try and bring objects from a higher orbit down to something below. But how do you enforce this? That's the other thing. You know, it's quite difficult, you know.
Great. Remember about the chat. Just to put the chat is already there.
Yeah,
and
I will.
I'll just put the link for the evaluation. It will be really interesting. It's also for us and also for the people who fund us. You see, we would like to keep this program running.
Okay.
And if we have, you see, good evaluation to the conference that are involved, well, we will keep it doing it. Okay.
Sure. I'm going to put that right here for the evaluation.
the participant just to do an evaluation. It's going to take just a few minutes. All right?
Sure.
Yeah, yeah. Probably we will be open for about more 10 minutes after
Sure.
we.
And if you have any questions, please, not just in
Yeah.
this presentation, but other things about space, feel free to ask me.
Yeah. Any question, guys? This is an opportunity just to open your eyes and to open, you see, we had an expert here working in Jet Propulsion Laboratory. Is one of the top centers in space. Any kind of vehicles they produce there, well, they're still flying, you see. The Vikings, they're still out there in the sky.
Yeah, especially Voyager, right? So Voyager exited the solar
Yeah.
system a few years ago, and it's been quite close to 40 years, just over 40 years actually, and it's the spacecraft that is I don't even know how many millions of kilometers it is, but the furthest man-made let's just say entity in space, so
what about that will be a good question. What about the energy, the atomic reactor that it has? You see, do you have any idea how long it's going to last?
I'm not sure if Voyager has, well, let me qualify atomic reactor. It's a isotope, right?
Isotope, right.
Yeah, it's a thermonuclear isotope. So what it does is it heats up the batteries, keeps the batteries warm so it can generate power. So one of the issues we find is the more we go away from the sun, the solar panels, because the efficiency would go down, right? So the further you're away from the sun, and once you exit the solar system, the solar panels are essentially useless. It just doesn't produce enough energy to. And being a spacecraft, there's constraints on how much power you can put, right? Think of your little, So you need very, very big ground assets, big giant telescopes to communicate. And the one in Canberra that I mentioned, the DSN, I think there was a picture there. It's about 70 meters. It's huge.
70 meters. Wow.
Yeah.
That's huge.
Yeah, unlike the Arecibo, which is kind of fixed on the ground, this one is fully tiltable, right? So it can track. Yeah.
Yeah.
So
Perfect.
yeah, and that's how it is. Now coming back to the question about energy itself. So it's very, very critical. You have to plan. And some of them, especially the Mars rovers, you need these thermonuclear, RTGs, radioisotopes. They can last up to 100 years, 40 years for sure, because the rover's there, right? So yeah.
Perfect. Yeah. That will be a nice project for the kid here. You see, to enter that area, how the spacecraft are going to be moving around.
Yeah,
moving around.
Yeah, and the propulsion tool in LEO and MEO and some interplanetary, it can carry fuel, right? Because the gravity is not constant, because, for example, at the Lagrange point, you hardly need any fuel, maybe a little bit, just for station keeping, just to keep it there. But if you want to change your orbit or change your trajectory, you will need to fire your thrusters. So most of the interplanetary ones use electric propulsion, so basically ions, right? And it's a constant stream of ions that's being fired and can keep the spacecraft going for years and years,
But perfect, guys. No questions then from Colombia, from Nicaragua, or from Honduras, Haiti. Yeah, we have several countries from Puerto Rico. Yeah, this is good. Yes, there is a question there. Is a question?
Yes.
Okay, identify yourself, please.
I'm Shmelinka Paul.
Right. Hi,
Okay,
Shamalinka.
yeah.
Okay, so I have a question for you. What discipline or subject we must concentrate on if we want to pursue a career in spacecraft, or what path shall we follow to attend this career?
Okay. And you're talking about, so are you in high school or are you in university?
I'm in high school.
Or in high school. Okay. Make sure you have a thorough understanding um, um, of physics, math, and other subjects, right? Especially physics and math, right? And if you have electronics, that's an added bonus too. And once you go into university, maybe look for aerospace engineering or aeronautics, astronautics, that sort of stuff. I have to admit, I mean, I've met people who've done history, right, and ended up in space. So there's no set pathway, but if you pick the ones that I mentioned, especially aerospace or aeronautics, you're kind of closer to what you'd want to do, Otherwise you'll go in circles and finally, it kind of shortens your path, if that makes sense. But make sure you have a thorough understanding of the basics, especially math and science, physics, and yeah. I would say if you have hobbies, most of the things that I see in myself and my friends is like I've always been into rocketry, right? Building rockets and trying to fly them, airplanes, especially model airplanes and things like that, and astronomy, that sort of stuff. So if you can supplement your studies with these hobbies, because studies can be a bit dry, really, really dry sometimes. If you don't like it, you just avoid it completely. But if you have hobbies where you get hands-on stuff, that is crucial. That will just take you from nothing to something much closer to where you want to be. If that makes sense. Does that answer the question?
Yes.
Good.
Thank you. Thank you for the question, Paul. Yeah. Yeah. Any other question, guys? Well, if we don't have any other question, I really appreciate, Aaron, your presentation, and
All right.
I would like to keep you in the loop for
Sure.
future conference. All
Yeah,
right.
sure.
Okay.
Yeah. Thanks for your
Take
time.
care.
And
Thank you
yeah,
much.
thanks everybody for your time, and hope this has inspired you to look at a career in aerospace, right? So
Yes, I'm sure that's the reason I select you as one of the speaker,
sure.
because the students are trying to just to select what they want to do in the future,
Yeah.
in the near future, really. And this will be outstanding stuff if they select aerospace. All right.
Yes.
All right. Yeah.
And before I sign off, I would say, you have to dream big. You have
Yes.
to dream big.
Yeah,
Otherwise, because America is going back to the moon. It's not just America, the Chinese are going, the Indians have landed,
yeah.
the Emiratis, UAE, they have Hope mission, and so
Yeah.
you have to dream big, because in the next 20 years or so, maybe in the next 20, 30 years, um, I would think going to the moon would be just as like right now going to the International Space Station, just like SpaceX flies in the Dragon capsule, so going to the moon. I mean, going to the moon is just 3 days. Going to Mars is 9 months. That's a different story.
Yeah.
But, over the years, technology will improve and it'll become more comfortable for people to undertake such journeys, So dream, dare mighty things. That's the motto of the lab where I am, right? So you have to dream big and try and do impossible things, So good luck with everything that you do.
Yeah. Thank you very much, Kai, and
All right.
keep going with your studies. All right. Take
Sure.
care.
Okay. Take care. Bye-bye.
Bye-bye. Bye-bye. Barak. Goodbye.